Alright, so I was just going to walk you through some of the practice problems we did in class today for those of you who either couldn't be there or if you want to take a second look. Just recall we're working problems that you could work with kinematics at first to set you up for the process for using energy to solve problems like this, and then we'll quickly move on to problems that with the types of kinematics we've learned so far we wouldn't be able to answer with kinematics alone. So we have a ball falling from rest from the top of this 12-meter building or whatever, and the question is how fast will it be going when it gets to the bottom? Well, of course, you know how to solve that with kinematics, but that's only because there's a constant acceleration. And so we want to find a way that would be a little more versatile and allow us to do some things a little more quickly. So we're going to use our energy arguments. And so the first thing I need to do is decide what system I'm going to use. Of course, I could include just the ball in the system, or I can include a ball-earth system. The first approach we're going to use is to select just the ball. And in the ball system, there's the force of gravity of the Earth acting on the ball. And so that's outside the system, and so I ask if that's going to do any work. And if you look at the direction of the force and you look at the direction of the displacement, they're both down, and so the angle between them is 0, so cosine of 0 is going to be +1, and so there will be positive work done by the gravitational force on the ball system. Well, of course, the work-energy theorem tells us that work done on the system will cause a change in energy in the system, and so now I just need to determine what the work is done, and that will be the change in energy. Well, since this is just a ball system, the only type of energy that we've learned so far that it can have is kinetic energy. And so the change in energy is going to be the final kinetic energy minus the initial kinetic energy. And work, of course, the definition is Fd cosine theta. So I'm going to substitute for work, since it's the gravitational force doing the work, with mg. And d cosine theta equals 1/2 mv squared, which is the final kinetic energy minus the initial kinetic energy, which was 0 because it started at rest. And then those masses on each side cancel, and I substitute for the gravitational acceleration, the gravitational field constant 10, and the displacement 12, and cosine the angle between them 1. Giving me the square root of 2 times 10 times 12 times 1, which is approximately 15.5 meters per second. And that's how fast it's going to be going at the bottom. Now, if I had chosen the ball-earth system, then a couple of things would change. First of all, notice how many forces are acting on the ball-earth system. Well, you might look at the free body diagram and say, well, we have the gravitational force, but recall that in the ball-earth system, the gravitational force is between two objects within the system, and so that's not going to act on the system and not going to change the kinetic energy of the system. So in reality, without air resistance, which until I tell you not to ignore it, you can ignore it, without air resistance, there's no forces acting on the ball-earth system. And if there's no forces acting on the outside on the system, then there's no change in energy in the system. Well, so the change in energy is 0, and change is final minus initial. That means that the change in energy Sorry, I had to pause there. That car next to me kept locking its doors and it was really distracting. So anyways, the change in energy is 0. So final energy minus initial energy is 0, which means the quantities of the initial energy and the final energy are equal. Well, what types of energy can a ball-earth system have? Well, it can have kinetic energy, but it can also have gravitational potential energy. And so I need to add the initial kinetic energy to the initial gravitational potential energy and know that that's going to be the equal to the final kinetic energy plus the final gravitational potential energy. And those are what we call the total mechanical energy of the system. Now, of course, the initial kinetic energy of the ball-earth system in this frame of reference is 0 because the ball is not moving and the Earth's not moving relative to this frame of reference, or it's not changing its motion. And so that's 0. But if I ask what's the gravitational potential energy of the ball-earth system initially, you should be asking me a question, and that is relative to what? Because you'll recall that all potential energies, gravitational potential energy, has to be relative to some point, and we have to define where that point is 0 before we can talk about how the gravitational potential energy is changing relative to that point. And so it's most logical to call gravitational potential energy 0 at the ground here, and so I'm going to call that 0, which means the initial gravitational potential energy relative to that point is mg times 12. And then the final kinetic energy, of course, is going to be 1/2 mv squared plus the final gravitational potential energy, which we just defined as 0. And so mg12 on the left side of the equation is going to equal 1/2 mv squared on the right side of the equation, where v is the final velocity right before it hits the ground. So substituting, I get 2g times 12 equals v squared. And that shows you that I get the same answer that I got before, which is a final speed of 15.5 meters per second. So now I'm going to just shift gears to a similar problem that we've worked before, an inclined plane problem. Only this time I'm not going to tell you specifically what the angle is, but if it were frictionless and you knew the angle, of course you could use your kinematics equations to find the acceleration and therefore find out how fast it's going to be going by the time it gets to the bottom of the incline. But again, we're going to try and use our work approach, and we need to select a system. This time I'm going to choose the ball earth system, or in this case the box earth system to begin with. And I ask, what forces are acting on the box earth system. And you see mg there, but of course mg is within the box earth system. It's a force between the two objects in the system, and so it's not going to change the energy of the system. But now I've got the normal force, and the normal force is of the incline on the box. That's not technically part of the box earth system, and so I have to ask if that's doing any work on the system. And the answer is no, it's not doing any work, because the direction of the force is perpendicular to the incline by definition. That's what a normal force is. It's a pushing force perpendicular to its surface. And the displacement, which is down the incline. Now again, this doesn't mean that normal forces can never do work, but in the case where the box is moving along the incline, the normal force will always be perpendicular to the incline, and so the normal force will never do work. And so if there are no outside forces doing work on the system, the change in energy of the system will be 0. And I could use the exact same approach I just used in the previous example. I'm going to take the final minus the initial. I'm going to break down the energies into the types of energy they can have, which is kinetic and potential. The initial kinetic energy is 0 because the box isn't moving. The initial gravitational potential is relative to what? Very good. And if I make gravitational potential energy 0 down at the bottom of the ramp, which is the most logical place to assign it, then that means it starts off with a gravitational potential energy of mg delta y. That, of course, is going to be equal to the kinetic energy at the bottom, because that's where the gravitational potential energy is going to be 0. And so substituting, I get 2 times g times 12 square root gives you the velocity, which again is 15.5 meters per second. Now that might surprise you at first that we got the same answer that we got for the ball falling, but if we think about it a little bit, it kind of makes sense in light of the energy understanding that we have now. The change in the gravitational potential energy of this system was the same in both cases. In the ball Earth system before, the ball moved 12 meters closer to the Earth, and so I had the same change in gravitational potential energy, which got converted to kinetic energy in that system. And the same thing happens here. The box gets 12 meters closer to the Earth here, and so it's going to have the same change in gravitational potential energy, assuming it has the same mass. And that changes into kinetic energy. And then, of course, both of those kinetic energies are proportional to the mass, and so for both of those objects are going to be going the same speed as long as they've changed vertical positions the same amount, which in this case was 12 meters. So we're just going to analyze that and confirm that with the box system alone. For the box system, of course, mg is acting on the box. Is it doing work? Yes, it is, because even though the gravitational force and the displacement are not in the same direction, there's part of them that are in the same direction. In other words, there is a component of mg, as we learned before doing our kinematics approach, there is a part of mg that's in the same direction as the incline. And so there's at least part of the mg that is in the direction of the displacement, and therefore mg is doing positive work. As we saw before, the normal force is not doing any work because it's always perpendicular to the displacement. And so the change in energy is due to the work done by the gravitational force, which is exactly, again, like we saw before. The only difference is now, instead of mg and the displacement being in the exact same direction, there's a component of mg that's in the same direction. And so that's where that d cosine theta comes in. That's going to find the part of the force and the part of the displacement that are in the same direction. And so looking at this picture, the direction of the force is down, and so I'm only interested in the direction of the displacement that is in the same direction or that is down. And so I'm looking for the change in vertical position, or y, which in this case was 12, just like before. And so mg times 12 equals 1/2 mv squared minus 0. Substituting and solving, I get a speed of 15.5 meters per second, just like in the previous example, and just like with the box Earth system. All right, so what's useful about these approaches is if I get a situation like this, where it's going to slide down in frictionless incline, but the incline is going to be curved. Now, with your kinematics that you've learned so far, you're completely at a loss here, because even though you can find the instantaneous acceleration at any point, if you know the angle at that point, that acceleration is constantly changing, and all of our kinematics approaches so far have depended on a constant acceleration. Well, this one has a constantly changing acceleration, and so kinematics would be a nightmare for us, at least at this point. And so what we want to use is a change in energy approach. And again, we can either choose the box system or the box Earth system. I'm going to start with the box Earth system and ask, what forces are acting on the box Earth system. And of course, there's mg that's acting on the box, but that's inside the box Earth system, so that would not do any work. There's a normal force, but notice, by definition, normal is perpendicular to the incline, and the displacement in this case will always be along the incline. So the angle between normal and displacement is going to be constantly 90 degrees, and cosine of 90 is 0. And so the normal force will still not do any work on this system. And so the change in energy for the system will be 0 because there's no work being done on the system, which means that the change in energy, if the change in energy is 0, that means the initial total mechanical energy is equal to the final total mechanical energy. What types of energy can it have? Gravitational potential and kinetic. And of course, where is gravitational potential equal to 0? We define that. The most logical place would be at the bottom, since that's where we're going to end up. Substituting, I get the gravitational potential energy is mg times 7. The kinetic energy, of course, initially was 0 because it started at rest. On the final side, the gravitational potential energy will end up being 0. The kinetic energy will end up being 1/2 mv squared. Doing algebra and solving then gives me speed at the bottom of 11.8 meters per second. Now, I might ask, what is the speed when the box is 2 meters above the ground, like this case in green? Well, I could start all over, and I could say, well, the change in height is going to be 5, and I'm going to define the gravitational potential energy as 0 at the 2 meter mark instead of down at the bottom. I could do that, but I don't have to. You see, what I've said by saying that the work on the work on the system is 0 is that the system can't change total mechanical energy ever. And so if I know the total mechanical energy at one place, in this case I found it at the top of the incline where the gravitational potential energy was mg7 and the kinetic energy was 0, then that's going to be the total mechanical energy everywhere. And so if I take that second point there, that 2 meters above the ground, I can keep the same gravitational potential relative point of the ground and just say, okay, well, when it's 2 meters above the ground, it still has 2 times mg joules of gravitational potential energy. And I'll end up subtracting that from both sides and solving for kinetic energy. Notice that's going to be the exact same result as if I had started over and said how much gravitational potential energy does it have relative to the 2 meter mark. Well, the change is going to be 5 times mg, which is exactly what we get when we do it this way. So that's one way that we can do that. Also, I could, introduce the idea of friction. If there was friction on this incline, and I told you that friction did negative 100 joules of work, that's just going to change this part right here, right? Instead of the work on the system being 0, it would be negative 100, and that would then equal the change in energy of the system. And so when I add an initial energy to both sides, you'll notice that the final total mechanical energy is going to be 100 less than the initial total mechanical energy. And so you'll see some examples like that on the assignment I gave you. But again, you're going to go the same way. You're going to use the same approach. And I mentioned in class, that we could also then run it backwards. We could have it have kinetic energy at the bottom of the incline, and as it slid up the incline, what would happen? Well, if I took the box or a system, there's still not going to be any work being done on the system, and so the total energy is going to be the same. All of that kinetic energy it has at the bottom of the incline is going to get stored as gravitational potential energy going up the incline, and I'd be able to solve from there. All right, thanks.